Hello and welcome to the New York City Category Theory Seminar. It's September 30th, 2020, and David Ellerman has spoken by our seminar, I think almost every year except one for the past 5 or 6 or something like that. He is going to speak about the logical theory of canonicity. Okay, David, take it away.
Okay, thank you. This talk is on a analysis based on 2 basic concepts, elements and distinctions. And so there's a lot of things that come out of this analysis. And I'm going to focus on canonicity, but that's not the only thing. We'll see there's a treatment of morphisms, duality, universal constructions, and it's all in sets. And then sets is sort of the basic category for category theory, and what we say here will extend automatically to the categories that are set-based, that have an underlying set functor. So what we start with is the duality between subsets and partitions. And partitions, you can think of them as quotient sets or covariance relations. And for subsets, we have the notion of elements of a subset. So the first question is, well, is there like a dual concept to the notion of an element? And we will see that the answer is the notion of a distinction. In the context of a partition, a distinction is simply a pair of elements in different blocks. So the blocks of a partition are what distinguish things. So distinction is a pair of elements. So I'm just now going to use these 2 concepts, elements and distinctions, or its and dits, if you wish. That's a play on the physicist John Archibald Wheeler's notion of its and bits. And so it's its and dits are basically the conceptual building blocks. So everything that we do here will come out of these two basic concepts. So you begin with, in the category of sets, to analyze what are the morphisms in the category of sets. And so we start off with the notion binary relation that transmits elements, and that's sort of the obvious thing. For each element in the domain, and you have an ordered pair in the relation, then there's some y in the codomain that's related to it. And then the notion reflects elements is just the other way around. Then you have the notion of transmits distinctions. So every pair of elements in the domain and a pair of elements in the codomain, if the x's are different, then the y's are different. So the distinctions are transmitted, as it were, by the relation, or some people use the language of preserved. The distinctions are preserved, and the reflections are just the other way. So when you have a pair of distinct elements in the codomain, then they're related to corresponding elements in the domain, then the elements in the domain have to be distinguished too. So that's 4 basic concepts, all just on reflecting and transmitting elements and distinctions. So what is a function? What is a set function? And usually you say a set function is defined everywhere and single valued, but defined everywhere just means it transmits elements. So we can say, use that language, it transmits elements, and to say it's single valued means it reflects distinctions. So that no one element can be mapped to 2 different elements because it reflects distinctions. So if you have a distinction in the codomain, then there has to be a distinction back in the domain. So a binary relation is a function, in other words, a morphism in the category of sets, if and only if it transmits elements and reflects distinctions. So this sort of interplay between elements and distinctions we're going to see throughout the whole talk. And then you say, well, what about the other important types of functions? You talk about reflecting distinctions, or what about if it transmits distinctions? Well, that's obviously injection, an injective map. And what about not only transmitting elements, but reflecting elements, and that's just a surjection. So these notions of transmitting and reflecting elements and distinctions not only single out the morphisms in the category of sets, but they single out the two different most important types of maps, injections and surjections. So that's sort of the first use of these concepts here. Now, the next thing is just, let's look at duality. And we've set up this thing where duality will just interchange these concepts. So when we normally think of the dual of a category, we think of the maps in the dual as being sort of abstract things. They're just the maps in the original category turned around. But in the case of sets, they're actually concrete binary relations, which the maps in sets op, the opposite category. And well, what do? Well, they do the opposite thing. They preserve distinctions and reflect elements. And we could call them a co-function if you want. So just by interchanging the preserves and reflects, or transmits and reflects, we go to the morphism that are in sets op as a concrete binary relation. And so that is the treatment of duality in category sets. And of course, all these things you're doing here with elements and distinctions will be abstracted in abstract category theory. So we're sort of analyzing and motivating these notions in the most fundamental category, that of sets. And as you know, the universal constructions just interchange the morphisms from the dual, and that just comes from interchanging the role of elements and distinctions, products, co-products, equalizers, co-equalizers, limits, and co-limits. And then you abstract that into abstract category theory. So this is the theme that we're developing here, is elements and distinctions are like a conceptual language, or the sort of atomic concepts by which all the constructions, the morphisms, everything in the category of sets are constructed, and they have this duality sort of built into them. So let's now try to focus in on the notion of canonicity. And from the beginning, category theory started with the definition of naturality. In fact, the original paper by MacLean and Eilenberg was not about universal constructions at all. It was about naturality. It was the general theory of natural equivalences. And so we have a mathematical notion of naturality, but we only have an intuitive notion of a canonical map. And this was pointed out and developed by Jean-Pierre Marquis a while back in a book on categories for the working philosopher. And Jean-Pierre said that, well, the intuitive idea of a canonical map is one that's made without any arbitrary decision. And he stated this is a quote from his paper, stated the sort of desiderata, what a treatment of canonicity would have to be. He stated in terms of limits and just dualized for co-limits. So the canonical maps are the maps that are part of the definition of a limit. And for example, the projection morphisms in a product, and in a, when you're talking about the universal mapping property, the universal morphism from a cone to the limit that's a canonical morphism as well. And then number 3, the unique isomorphism between two candidates for a limit. And that's really a special case of 2, if you wish. But those are the maps that we need to explain. And I will give a definition, a treatment of canonicity that will pick out and explain exactly these maps for limits, co-limits, and so forth. So the way the analysis proceeds is that you have these two logics. You have the ordinary Boolean logic of subsets, and then you have the logic of partitions that I've talked about before in this seminar. over the years. And it turns out that canonicity really, anything that's canonical goes back to these two basic logics. They're sort of like twin backbones, mathematically speaking, for the category of sets. So we have, and in fact, all we need really is the lattice structure. We don't need the implication operation on subsets or on partitions. And so we're going to basically deal with the two lattices. And the Boolean lattice, of course, is the ordinary power set Boolean algebra, in fact. And the important thing here is the partial order. And the partial order is inclusion for sets. All that's very trivial. And notice that the partial order induces a canonical injection. So that seems totally trivial. It's not as trivial in the case of partitions, but this theme that the partial order in these two lattices induces canonical maps, that is basically the theory. And that's what we'll see holds throughout all the universal constructions in the category of sets. And the other sort of backbone here, the other dual lattice is the lattice of partitions. And the partial order there is the refinement of partitions. And you can think of this two ways, that each partition has a set of distinctions, namely all the ordered pairs that are in different blocks of the partition. And refinement just means that the less refined one, all its distinctions are included. And so you have like subsets operate this way, and each element of S is an element of T. And for partitions, each distinction of sigma is a distinction of pi. So we see here again, this close connection between elements and distinctions. Or you can think of it, refinement, this is the refinement symbolism, that every block in the more refined partition pi is contained in a block of sigma. So that's the other way too, that's the usual definition of refinement in the lattice of partitions. And I would just warn you that a lot of the older literature wrote the lattice the other way around. They called the relationship refinement, but it was really unrefinement. It was, in other words, they were thinking of they were thinking of a partition as an equivalence relation. And so here I'm very specifically talking about a lattice of partitions, not a lattice of equivalence relations, which are just opposites of each other. So the claim that we're trying to demonstrate here is that all canonical maps and sets arise from these two maps, that the map induced by inclusion and the map induced by refinement. Because when you have refinement, then every block in the more refined partition is contained in a block of the less refined partition, and thus you have a surjection. Pi, every block in pi maps to a block in sigma. So you have two ways in which the partial order in these two lattices generates injections and surjections, and we'll see that all the canonical maps in sets arise from these two ways. So they, as it were, go back and are based on the logic that's behind the mathematical structure, and that's why they're canonical. That's the argument. I can't prove it, because canonical is an intuitive idea, but we can certainly demonstrate it. And so the paper goes over all the different cases. I'll go over some of the cases here, just to sort of give you the sense of it, but it's pretty tedious to go over all the cases. So let's just start with the most basic universal objects and constructions in the category of sets. So we have a partition. Partition is a set of blocks, and we assume we don't assume, I mean, the most refined partition is the partition of singletons. And so each block is just a singleton, and every partition is refined by one, the one sub U. And so you have a canonical surjection, from U into any partition on that set, where the singleton of small u here maps to that whatever block it's contained in. So it's a obvious map. In the bottom of the lattice partition lattice is the indiscrete partition, which is just everything. There's only one block. It contains the entire set. And it is refined by everything. So it's the least refined. So everything is blobbed together. And as a set, this partition is a singleton. It's a one element set because there's only one element in it, namely this block, which consists of all of U. And since every discrete partition refines it, that means there's a canonical map from each element of U, the elements of U are just represented by singletons here, to this one element set. And that's, of course, why the one element set is the terminal object. So we've shown that the terminal object map is just this map from every discrete partition, any set U, in other words, the elements of U, to this one element set. So that's how the terminal logic is explained as a result of this canonical surjection. And then we go to the other lattice, the Boolean algebra, power set of U, and every subset is, the top of it is, of course, U itself, the set U. Every subset's contained in it, so you have a canonical injection into U. And the bottom of the subset lattice is the empty set. So that means since empty set is contained in every set, that means there's a canonical injection from the empty set into any set. And that's exactly the property that makes it the initial object in sets. So we see that two dual notions of terminal object and initial object arise from the bottom of these two lattices, the indiscrete partition, the bottom of the lattice of partitions, and the empty set is in the lattice of subsets. So this is just summarized here in the table, that duality between elements and distinctions, between inclusion and refinement, and then the canonical maps. Inclusion induces this canonical map, refinement induces this canonical map. So your extreme objects arise from the empty set being included everything. So you have this canonical map here that makes the empty set the initial object, and every partition refines the indiscrete partition. So you have this induced map here that makes the one element set into the terminal object. So that's the two extreme objects. And then we go on to let's see where we get the epi-mono factorization in sets. So we give it a function now. The function is the data we're working with, and every function induces this inverse image partition on the domain, or called the co-image, some people. And every block in that partition is I should have a Y here. Every block in the partition is an inverse image of a Y. That's a typo. And the image of the subset is inclusion here. So we have these two things to work with. And since this inverse image partition, the co-image partition, is refined by the discrete partition on X, then there will be this induced surjection from X. Remember, each element here of this partition is just a singleton, so it's an element of X. So it gets mapped to the block, and that gives us this surjection here. And then the rest of it is just the image is contained in the codomain Y. So you get a canonical injection here. And that's the epi-mono factorization. So the epi-mono factorization comes from the refinement here and the inclusion here. And as you would expect. So all the canonical maps that are surjections come from this refinement relation in the lattice of partitions. All the canonical maps that are injections come from this simple inclusion relation. So that is the analysis that explains those basic concepts. And then we say, okay, let's now start with the other universal constructions, the coproduct. And first of all, I would say, have you ever wondered why product and coproduct? I mean, what's so dual about these two concepts? And it turns out that they are simply given two sets. There are the set of the maximal set of elements, and of course the product is going to be the maximal set of distinctions. So elements and distinctions come in here just to explain the very concept of the coproduct in sets, and dually distinctions, maximum number of distinctions you can make given two sets are the elements of the product. So let's now just work this out for the coproduct in sets. So the first point is that your two sets, X and Y, they might overlap or might even be the same set. So to construct this maximal set of elements you can get from two sets, you have to ignore, as it were, the overlap. And one way to do that is just to sort of make a copy of all the elements of Y. And so you put an asterisk on them. And then you take the union of these two sets. So even if they overlap, the overlap's going to be in both things. You're getting the maximum number of elements from these two sets by this construction. And of course, then you have your inclusions. And as you know, inclusions give rise to canonical injections, and those are the canonical injections of the two sets into the disjoint union. Then the universal mapping property. So we assume we have two maps from our sets X into some other map Z and Y into Z. So it's usually called a cocone. And we want to construct this universal factor map. And we have the usual diagram here where we have our disjoint union. We have the two canonical injections into it. We have this cocone of F and G here. We want to say, how can we construct this canonical map from the disjoint union to Z so that these triangles commute? So, so here's how you do it. So the map F here, here's F, it contributes this co-image or inverse image partition on X, F inverse here, and G contributes a co-image partition here. So that means you have a partition on the disjoint union, just combine the blocks of these two partitions on X and Y. So you have a partition there, and so then you look at, okay, on this set, we have this partition. It's refined, of course, by the discrete partition on the disjoint union. That means we're going to have a canonical surjection from each element of X, this disjoint union Y, to a block here. And what does that look like? Well, consider any element in the disjoint union. In other words, a block in this discrete partition on the disjoint union. It's contained in a unique block of either this form or G inverse of Y. So it's contained in one or the other of these, and so that defines your map. You take the W to either X or to Y, and or and that's your that's your definition. So let me go back here. This is the way this canonical map here is defined, and I've got a bad notation here. This should be F of Z and Z, and so your map is really going to W to Z. You should always give a talk on slides before discover these little typos in the slides, so I apologize for that. So G inverse is of some Z, F inverse is of some Z, and your W here is contained in one of those, so the map goes to that Z. And that's this canonical map here. So that gives us this refinement surjection onto the image. It goes onto the image of these two things in Z, and then you have just this injection here completes it with the, gives you the map. So that's the way your map is constructed. The canonical surjection followed by the canonical injection gives you your factor map in the coproduct construction in sets. So now let's do the dual analysis. So instead of forming a construction given two sets of the maximum number of elements, let's form a construction the maximum number of distinctions. In other words, pairs of elements you can get from two given sets, X and Y, even if they're the same set, even if they overlap, and so forth. So the usual construction, as you know, is a Cartesian product, a set of ordered pairs. But let's show that there's, the real point is all the different pairs. So let's use the same trick here and mark all the elements of Y by our asterisk, and then take the set of unordered pairs, X and Y. So I just use a little symbol here for unordered pairs. That's isomorphic to the Cartesian product. And it really brings out the fact that what we're really doing here is taking the maximum number of distinctions, the maximum number of distinct elements, even when X and Y are the same set. The same trick we used trying to get the maximum number of elements in the coproduct construction. So whichever way we construct it, we have the set X, and that defines a partition indexed by each element of X. Here's the partition on, I'll just use X cross Y here, where the element X is crossed with whole of Y, and the block in the other partition is each element of Y here. So these are two partitions on the Cartesian product. So you know where this is going. Those two partitions are each refined by the discrete partition on the Cartesian product. So you have two induced surjections taking each pair here to the appropriate block that it's contained in, and those are precisely the projections. So the projections are in fact defined by the refinement relationship between those two partitions and the discrete partition on X cross Y. So that defines your canonical maps associated with the product, and then you have to go, let's do now the universal mapping property for the product. Here I just give a description of it. We have a cone, two maps from some Z to X and to Y, and we want to define this factor map here.
David?
Yeah.
Okay. That's good. Can I just, maybe I missed, maybe you, can you just go back, please, to the previous slide?
Which one?
Yeah, this one. Maybe you commented here, but I missed it. So when you say X times Y to X on the first bullet, you say it's a surjection, but it might not, hang on, if, for example, if X is 1 and Y is 0, then PX is not a surjection.
Really?
So it's not a surjection in general, that map.
So what's the cross, what is the Cartesian product of the empty set and a set?
Right, so if X is 1 and Y is 0, then PX goes from 0 to 1, so it's not a surjection. That's all I'm saying.
Well, what is the Cartesian product of 1 and 0?
0.
Yeah. And isn't
right,
that?
X is 1 and Y is 0. And you said Px goes from X times Y to X. So therefore Px goes from 0 to 1. So it's not a surjection.
Well, let's see. Let's go back here to our. Yeah, the definition here is for each y, small y in Y, you have this partition. Then you're saying, suppose there are no elements in Y.
Yes, but there is an element in X because it's singleton.
So what is the partition?
Can't you just assume that X and Y are not empty?
Yeah, you can, but Paul may be right that this construction assumes an element in Y, ditto for X, and so you get the map, but it's not a surjection. That's your point?
Yes.
The 1, 0, 2. Yeah, that looks, so that this looks like an exception to the, we get the canonical map, but we don't get it as a surjection because the domain is empty.
Right.
David, earlier you gave a characterization of what you said were surjections in terms of elements and distinctions, right? And it was a
right.
complex characterization, right? So it may be that when you're talking about surjections, you're talking about things that sort of preserve or reflect, but when you're in this setup where you're looking at elements and distinctions, the mappings of what preserve and reflects mean act differently on empty objects. I'm not suggesting we solve this now, but I'm saying that might be sort of how that works out.
Yeah, that was here. Yeah, these definitions obviously assume non-empty sets.
Do they? Where? They don't. These definitions here assume non-emptiness. How? They didn't seem to assume that, as far as I can see. So you said that reflects elements means surjectivity, right? So that's fine. I mean, that doesn't depend on X and Y being non-empty. That second bullet will indeed characterize surjectivity.
I just wanted to check. I didn't mean to lead us too far astray here. There's a question.
I mean, the notion transmits elements assumes for each element X, it's transmitted. And you probably have to treat specially the case where your domain is empty. So you have no elements to transmit or to preserve. That's it.
Well,
here.
No, I mean, the first condition says that R is total, and the second condition says that R is surjective, right? That's that's true generally. That doesn't depend on anything being non-empty. And the third condition is what? Injectivity, and the fourth condition is single valued. None of these facts depend on X and Y being non-empty.
Yeah, in the sense, this is an if-then statement. So if the antecedent is empty, then it holds. Mm-hmm. Yeah, okay, we got to look at all these very special cases.
It's just a question. I didn't mean to lead us there, but.
Yeah.
Certainly, I think throughout there's been an assumption, which is why it all of a sudden rears up.
Okay. So here we are, these canonical projections, which in the special case need not be surjections. So now I want to try to show how to get the universal mapping property for the product here. So the data is this cone, and we need to construct this canonical map from the tip of the cone into this Cartesian product. So F contributes this partition on Z, G contributes a partition on Z. So you have two partitions on Z, then you just take their join. And this is the operation, the only operation we actually use in the Boolean or the partition lattice is the join operation, aside from the partial order. And the join of two partitions is a set of all non-empty blocks of this form. So each block is indexed by an element of X and indexed by an element of Y. So we wanted to find this unique factor map. We have now we're working on the partition lattice on Z. So the disjoint or the discrete partition on Z refines this thing here. So every Z, there's a block that is contained in. Every singleton is contained in some block because it refines it. And thus the factor map will take Z to that X and that Y as an ordered pair in this image. And the image is included here, and then the rest of the map is just the canonical injection there. So that's the way you construct the factor map, unique factor map in the product using the underlying partition structure given to you by your inverse images. Okay. So now we move to co-equalizers, and the data here is not two sets, but two parallel maps. And for each element X, we got a pair of elements in Y. And so we define an equivalence relation on Y generated by this Fx identified with the G of X. And so once you generate that equivalence relation, that's just like, you can always think of that as just the intersection of all equivalence relations containing these pairs of elements in Y. And then you take the quotient set. So I indicate the equivalence relation by this tilde here. And so that's a partition on Y. It's refined, of course, by the discrete partition on Y. So you get a canonical surjection from Y into that. And so that's the definition of the canonical map in the co-equalizer. And now we want to do the universal mapping property. So we have the data now is another map Y to Z, so that this holds here. We wanted to find a canonical map from this co-equalizer to Z. So the triangle here, this triangle commutes. So how do you do that? Well, you got the picture here. We already have a partition on Y, namely tilde, and we have that this map H satisfies this condition here. That means that that H must identify at least f of X and G of X, because H of F equals H of G in Z here. So that means in the partition lattice on Y that this H inverse, this partition on Y, has to be less refined than tilde, because it identifies f of X and G of X and maybe identifies other things. So we have a refinement here, and that means we get a map surjection from the blocks of tilde to the blocks of H inverse. So each block B in the partition tilde, there's a unique block, H inverse Z, containing it. And so you simply take your map going from this block, which is an element in the quotient set, to Z. And then that takes you to the image, and you just finish it up with the inclusion. So that's the way H star, your factor map, is defined. So you see here the standard treatment, that it's defined by refinement, then followed by a injection. And that's how you get this factor map here. So you're really using the refinement relation in the partition lattice on Y to say that this partition is more refined than the one induced on Y by this, and therefore you have your induced surjection onto the image, and then you follow up the image with the injection. So that's the co-equalizer. And the equalizer is even simpler. You've got your two parallel maps again, but now you take the subset of all the x's where the two maps have the same value. and that inclusion gives you this canonical map here. And then universal mapping properties, you have some other map H so that this holds. And and you want to define this map from Z into the equalizer that will make this triangle commute. And of course, this is even simpler. The image has to satisfy this. So all the elements, the image of H of Z and X have to be where F and G agree. So the whole image is included in the equalizer, and the canonical map is just the inclusion. So here it's even simpler. We're not using the partition lattice, we're using the Boolean lattice to give us our canonical maps. So the theme here is that all your canonical maps come from one lattice or the other, and that's what makes them canonical. They go back to this logical structure that stands behind the category of sets, the two dual lattices. So we've now done products and coproducts, we've done equalizers and co-equalizers. So we know that this elements and distinctions analysis and treatment of canonicity applies to all limits and co-limits, because that's all you need are products and coproducts and equalizers and co-equalizers. But I thought I would do, in the paper I work out both push-outs and pullbacks, but let's just do the push-out so it doesn't get too tedious here. So the data for the push-out, we've got two maps from common domain into X and Y, and we have the injections here into the coproduct. And so we just then we have two parallel maps now. And so we take the co-equalizer of those, and tilde here is again the equivalence relationship on the disjoint union. And so you can define tilde as whenever there's a Z such that F of Z gives you X and G of Z gives you Y, then you identify X and Y, and you take the equivalence relation, tilde's equivalence relation generated by that identification. So now we have the canonical maps here from X into this co-equalizer, the Y into this co-equalizer. And so that gives you these canonical maps here. And we want to now construct the universal mapping morphism here. And the data then is a map X to U, Y to U, such that this all commutes. So this is the push out square. So once again, we use these maps to take the partition. So we have H inverse is a partition on X, H prime inverse is a partition on Y. So we have this disjoint union partition on the disjoint union. But remember, we're working with a co-equalizer here on the disjoint union. But the very condition of these two maps is that this here has to hold. So that means that once again, this disjoint union partition is less refined than tilde. It has to identify the things were identified by tilde by this condition. That's what the condition means in terms of partitions. And that means that tilde refines it. It's less refined than tilde. So every block in tilde is contained in a block either of this form or this form, and that defines your factor map, the H star into the images, and then as usual, the images give you the rest of the map, the injection part. So that's how you get your factor map for the pushout. So the same theme we've seen throughout this is that these canonical maps are defined by reaching back to the lattice structure, the two dual logics, two dual lattices, the Boolean lattice of subsets and the partition lattice on the sets. So that's the basic idea of so you not only get this treatment of universal constructions in sets, but you get the definition of all canonical maps rise from these being defined either by inclusions in the Boolean lattice or by refinements in the partition lattice. So that sort of is the basic treatment of category of sets. And then the question is, how does this extend to set-based categories, groups, modules, fields, whatever, any category that has an underlying set functor, concrete category in that sense. And the idea there is that any morphism in those structured sets is counted as canonical automatically. That because the structured sets are defined by, group is defined by the composition relationship and so forth. So that's canonical. And then the fact that it's a structured set allows you to then go back and use the universal mapping properties in sets, and which we've already analyzed. And you put that together, and then that gives you the analysis of canonical maps in categories of structured sets and so-called concrete categories. And so Jean-Pierre Marquis gives an example of this. He says, suppose you have a category, finite products, finite coproducts, and a null object, an object that is both initial and terminal. Then you can define a canonical morphism from the coproduct to the product in such a category. So let's think now, if you're just starting with some abstract category with these properties, and it has finite products and finite coproducts, then you're not going to be able to analyze in terms of sets because you're not given any basis from the objects in this category, but you're given as a part of products and coproducts. A null object, you're given canonical maps. And so canonical morphism would be any one constructed from those canonical maps. But let's do better than that. Let's go look at a category satisfying these properties that is set-based. And the simplest set-based category is just the sets with a designated element. So this is the so-called pointed sets, sets asterisk here. So it's like the category of sets, except each set has a designated element or base point given to you by such a map, one into the set. And that is by definition canonical because that's structural. That's like the composition or whatever in the category groups and so forth. So a function, a morphism in this category is simply a map between the sets that preserves base points. So it makes this little triangle commute. So this is the slice category of 1 over sets, if you wish, or sets under 1. So I don't know if I should go into all the detail here, but basically what I do is just to now apply the set-based analysis we've already done and show that all the canonical morphisms that you need in pointed sets come from the definition in sets plus the base point maps, which are by definition canonical. So I show here how you get the terminal logic. The 1 point set is both terminal and initial here, and then I show how you get the products and co-products, and then go through the whole construction. So I think it's a bit tedious to go through all that here. I've taken up 45, 50 minutes now. So I go through that whole thing. Slides are available. Newsom has a copy of the slides.
They're on the webpage.
They're on the webpage, okay. So you get all these canonical maps, and finally you get the canonical map here. So I take Jean-Pierre Marquis' very example and show how this analysis fits it. So, and then you say, okay, what happens in an abstract category? Well, the atomic canonical maps are the ones that are assumed. If you assume you have products, then you assume you have the projections and the unique factor maps, and they're all canonical. And then anything you could get by composing those is a molecular canonical morphism. So, we've done the analysis in sets, we've done the analysis in a set-based category, and then in an abstract category where the objects are not set-based, then you get the canonical maps just as part of the definition. So what you assume you have, products, co-products, and so forth. And so there's nothing to be said there. So finishing up here, I call this the logical theory of canonicity. The logic refers to these dual mathematical logics, the Boolean logic of subsets and the logic of partitions, which we've seen play an equal role. I mean, they play a dual role in limits and co-limits, equalizers, co-equalizers, and so forth. So both of them are sort of equally fundamental mathematically, and even the notion of duality comes out of that. So one interesting question is where does the duality between subsets and partitions come from? Well, they're category theory duals, but in a sense, we've already explained how the category theory duality comes out of this elements and distinctions, interchanging the role of elements and distinctions. So you could also say that we've explained, in that sense, the duality in category of sets, and but whatever way you look at it, you have that duality, whether you say it comes from elements and distinctions or vice versa, it's there. And so that's the interplay. We treated morphisms, we treated duality, we treated canonicity, and we treated the universal constructions, and we treated how it generalizes into set-based categories, and then you abstract the whole thing into abstract category theory. So this is essentially my last slide. You start, any construction starts with certain data, and if that data is sufficient to reach back into those two basic lattices and to define inclusions or refinements, then the maps that result from that are the canonical maps. And we've seen how that holds throughout all the canonical maps in sets, and then you can generalize that to set-based categories. So that's the treatment of canonicity. And that's basically my talk.
Thank you very much. Any questions? Any discussion?
I want to thank Paul for pointing out I got to be more careful on the special cases of empty sets here.
I'm a bit of an empty set obsessive. Actually, I have something to ask. So when you started your talk and you were talking about distinctions, I was a bit surprised because having had my mind warped by intuitionism, I tend to think of injectivity more about as reflection of equality rather than preservation of distinction. So I assumed that as your talk developed, everything would be very, very classical, but actually it didn't seem like that. The distinction, the concept didn't seem to come back in the rest of the talk. So it didn't really seem to matter that you started with this very classical thing. Everything else seemed to be perfectly intuitionistic.
Well, you're saying I could have, rather than said reflect distinctions, I could have said preserve equality, so that one thing never gets mapped to two things. Is that the point? Your mic is off, Paul. Your mic is off, Paul.
Sorry about that. Intuitionistically, you wouldn't say it, Nick. You wouldn't say one thing doesn't get mapped to two things, but you would say equal things are mapped to equal things, or alternatively reflect equality. So injectivity would be reflection of equality. Yeah, both of those conditions would be swapped around. But that change doesn't seem to affect anything that you did subsequently.
Yeah. I mean, there's a whole other bit of things I didn't talk about here, and that's the information theory. We have these two lattices, and the quantitative version of the Boolean lattice is just the normalized number of elements in a subset, Laplacian notion of probability, discrete probability. And you can do the same thing for the lattice of partitions. It's the normalized number of distinctions in a partition give you the information in that partition, because information is about distinctions. And that's why I develop everything using distinctions and not equality. And the opposite, I mentioned the way the lattice of partitions is often turned upside down, for example, in Garrett Birkhoff's book, because he's really thinking of equivalence relations. So what I'm thinking of is the complement of an equivalence relation. And the complement of equivalence relation is what's called an apartness relation, I think in the intuitionistic stuff. And it's just the set of distinctions of a partition. So the equivalence relation is a set of things identified in a partition, namely all ordered pairs that are in the same block, and distinctions are all the ordered pairs in different blocks. And so, and that's what I lectured on before, was this logical theory of information, which underlies the Shannon theory. We derive the Shannon theory as a certain transformation of the logical theory, and the logical notion of entropy is a measure, unlike Shannon entropy, which is not a measure. That was sort of the subject of my last talk. And so that's, I mean, if you're asking why I focus on distinctions, that's why. It's got implications, and a whole new theory of logical theory of information that subsumes the Shannon theory that I published several places.
I was wondering if you get anything more by going, instead of working in the category of set, but working in the category of relations, simply because then you don't have to deal with co-functions. The opposite category of relations is relations. So,
well,
but most operations, like you said, most categorical operations are somehow set-based, not rel-based.
Yes, that's why. And the original result that got me thinking about elements of distinction was that treatment of functions as preserving elements and reflecting distinctions. And so Then I started thinking, well, can I analyze, universal mapping properties in terms of that? And everything sort of fell in place. And so that these notions of elements and distinctions really are fundamental notions that are the sort of atoms, atomic building blocks of subsets in the one case and partitions in the other case. And those two lattices stand behind, as you see, morphisms, duality, universal constructions, and canonicity.
Any more questions?
A rather, I don't know, strange observation, because I've been playing with RHEL and finding some difficulties there and whatever, and thinking about it, would be, maybe that's a way to maybe think about this canonicity thing, is when you pick out sort of what the nice canonical maps are in RHEL and look at how they compose, then you really don't get like, things that factor into everything like you do in set. And instead, when you pick out the factory stuff, you actually tend to get back the set like stuff back. If you're looking, because, where it's in set, like, you have all this nice stuff about how you can, build everything up canonically. If you look at what's sort of canonical in terms of composition of properties in RHEL, you get back, there's a nice paper that I don't have handy that breaks down ways of picking out different sets of functions and co-functions and little bits and pieces and all the different subsets you can build back out of RHEL, or subcategories you can build out of RHEL, looking at only different classes of maps as canonical.
Yeah, yeah. I haven't worked through that, but that sounds right.
Pointing.
I'm sorry, I didn't hear that, Kirsten.
Just recalling back, one of the ones that emerged where if you pick out things that, some of these combinations of preserves and transmits in the right way, one of the ones you get back is pointed rather than just pure set.
Anyways, if there's no more questions, let's thank the speaker again. And,
can I just have yeah, sorry. I was just so this is a brief comment and sort of a reinforcement of I just wanted to say that
Mio, you're coming in really bad.
Yeah, you're really breaking up.
Mio, you're coming in really bad.
I'm sorry. Yeah. Let's see. Is it better now?
A little bit.
Yeah, I think it's also kind of bad on my end. So I was going to say that this behavior of the empty sets should perhaps not be too worrisome. There are other situations where things work in the categories where the initial or terminal object behaves a little different when you do
Mio, we're really not making it. I'm not making it out. David, you making it out?
No, I'm not.
And you take the
anyways.
yeah, I don't know. You guys still don't hear me?
No, not really. Sorry.
Okay. So, yeah, I'm gonna give it just one last try, and if it goes fine, otherwise maybe next time. So, in the category of commutative algebras, if you take the tensor products, okay, I'll try muting it on YouTube. Stopping the video, maybe this works better. So, in the category of commutative algebras, if you take the co-product of and you have non-zero algebras, then you also always have the canonical maps are always injective in monomorphisms. But as soon as you take a non-zero algebra, tensor product zero algebra, then you get one of these maps that actually become non-injective anymore. So I think things like this happen in other categories where if you replace an object with a trivial object, then it becomes no longer has the property it has.
All right. Anyways, Mio, I think he's talking about other more algebraic categories. I think we should thank this speaker and invite him back to speak again. He's come every year, and I think he should continue. I loved watching this develop over the years. It's really nice. Anyways, thank you very much.
All right.
Okay, I think we have a speaker next week, or well, anyways, you'll look it up on the web. It's a pleasure. I hope you're all okay. Thank you very much. Take care.
Thank you.
Good night.
Thank you.
All right. Take care.